Hi everyone, welcome back. This is our last lecture on recurrence relations. We're going to look at divide and conquer algorithms, and we're going to see how to analyze them using recurrence relations. Now, the difference with what we've done up till now is that the recurrence relations we've studied have all been linear with constant coefficients, and specifically we've been looking at first order and second order recurrence relations. In this section, the recurrence relations that come out will not be first order or second order. In fact, they'll be a little bit different than what we've seen before, but we can still use the techniques we've developed so far. And these recurrence relations are the ones that come up from studying a class of algorithms known as divide and conquer algorithms. So this material does correspond to section 10.6 of Grimaldi. However, we have written up a set of notes that covers this material, and it's available on Canvas. It's actually a part of the notes booklet in section 4.4.2. So refer to the notes booklet, section 4.4.2. So that's the fully worked out details of what I'm presenting here. In section 4.4.1, there's the templated lecture notes, which you can fill in as you follow along with this lecture. But in 4.4.2, we've expanded upon all of that and gone into further details on everything I'm about to do in this lecture, and even some more. One thing we won't cover, that's covered in section 10.6 of Grimaldi, is we won't cover big O notation. There it's covered a little bit more formally. I'll mention it here, but I'm not going to go into detail on big O notation. It's not really a topic of Macm 201. So here's our fundamental question we're interested in to start with. What is the fastest algorithm for sorting an array of n numbers? We've already looked at one algorithm for sorting an array. That's the bubble sort algorithm. And in exercises, we've also looked at another one called the selection sort algorithm. So we've seen two algorithms for sorting an array. We're now going to introduce another sorting algorithm called the merge sort algorithm. Now, why so many different algorithms for sorting an array? Well, bubble sort, as we worked out, can sort an array of length n by doing n times n minus 1 over 2 comparisons. Selection sort, as you worked out in the exercises, also does the same number of comparisons. However, merge sort, which is the algorithm we're going to talk about now, can do it in n log base 2 n minus n plus 1 comparisons. And you might say, okay, is that better or worse? It's kind of hard to compare those two. Well, the key feature is the following. If I expand this out, this is n squared, and then maybe I'll put a half in front, minus 1/2 n. So if I think about what happens as n gets large, what's the dominant term? The dominant term is this n squared. It's actually the 1/2 n squared is the dominant term, but really the key feature is n squared. So the number of comparisons that are done on an array of length n is on the order of n squared. What this means is that if I double the length of the array, I should expect 4 times as many operations to be done to sort that array. So it scales like n squared. On the other hand, the merge sort, the dominant term is this n log 2 n. That's not quite n squared. They both have a factor of n, but whereas the bubble sort has a second factor of n because it's an n squared, this one has a log base 2 of n, which grows slower than n. So that means the merge sort algorithm uses fewer comparisons. How many fewer? Well, as we scale up the value of n, we can see exactly how many fewer. So here's our table indicating for a length n array, this is how many comparisons bubble sort does. This is how many merge sort does. And in order to make the calculations easy to do, in other words, to take log base 2 of n, we're just going to use n as powers of 2. So when n is 4, an array of length 4, bubble sort does 6 comparisons, merge sort does 5. Okay, so it does 1 less comparison. It's not going to be much of a time saver. But time savings really comes into play the longer the array is. If bubble sort, or if we're doing an array of length 16, bubble sort will do 120 comparisons, whereas merge sort only does 49. For an array of length 64, bubble sort does a little over 2,000, merge sort does a little over 300. For an array of length 1024, bubble sort does over 500,000 comparisons, but merge sort is less than 10,000. For an array of length 10 to the 6, bubble sort does approximately 5 times 10 to the 11 comparisons, whereas merge sort does 20 times 10 to the 6. So merge sort does a factor of over 25,000 fewer comparisons. So merge sort is a lot quicker on longer arrays. How does merge sort work? So that's what we'll get into. We'll get into how does the merge sort algorithm work, and then how to compute the number of comparisons it does. So in other words, how to compute the cost of running the algorithm depending on the length of the input. So the way merge sort works is it does the following. It takes this array, so let's look at this one up here, for example. What it does is, the first step it does is it chops it in half, or roughly in half. So here, maybe chop it like this. So now I've split it up into two arrays, 9, 3, 11, and a 2, 6, 13, 5. And then what it does is it sorts this array, and it sorts this array. So it sorts the two halves, and then it merges them together. And so once those two halves are sorted, it's kind of a simple step to merge them back together to form the fully sorted. So here's what merge sort would look like in practice. It would take our array, 9, 3, 11, 2, 6, 13, and 5. It would split it up into a 9, 3, 11, a 2, 6, 13, and 5. We'll call this the left-hand array and the right-hand array, whereas the original array was A. Then it sorts this, and it sorts this. Now you may say, well, if we can just sort an array of length 3 and an array of length 4, then why couldn't we have just done whatever that sorting is that's done at this stage? Why didn't we just do that originally? And the answer is, we do. The way we've done this here is this sorting is a recursive call to the sort algorithm, the merge sort algorithm. But for right now, we'll just say it sorts it. So what it does is it sorts it 3, 9, 11, and then 2, 5, 6, 13. And then once those arrays are sorted, so there's our sorted left and right arrays, then it merges them. And the way it merges them, it would scan through and it would go, okay, so of my left and right array, which one has the smallest value? And because they're already sorted, it just has to look at the first value of each. And it sees the 2 in the right array, so it takes it. And so we've dealt with that one. And now what's next? Next it'll say, oh, there's a 3 in the left array, so it's dealt with that one. And now it just has to compare again the first values of the remaining arrays. And it goes like that, and so on. So it'll go 5, and then smallest between 9 and 6 is 6. And smallest between 9 and 13 is 9. And smallest between 11 and 13 is 11. And one of the arrays has now been all used up. So then it just takes the remaining part of the other array and sticks it on the back end here. And so that's 13. So that's the merge sort algorithm as a whole. It splits the problem up into two subproblems, and then does a recursive call to the merge sort algorithm. And then once it sorts those two halves, then it merges it together. So there's sort of those two main steps. Split up into two smaller problems, recursively call the algorithm, and then reassemble. What I'm going to focus on first is this merging, this reassembly. And so we'll focus on that part. That's what we're going to call the merge function. And so here, the idea is we've got an array, like we had on that previous example, and it's been split into two parts. And rather than me actually listing these two arrays, a left array and a right array, I just need to say what is the index that the left array is going to range over and what are the indices the right array is going to range over. And so that's where these three numbers come in. So the left array goes from L to M, and the right array goes from M to R. So that's what we've indicated here. We've got one array that runs from 1 to M, or sorry, L to M, that's an L to M, and the other one that goes from M plus 1 to R. So they're not going to share that value AM. This one, this right half, actually uses the next element of the array. And so then what we do is we build those two arrays, the left array and the right array, so that's here. So that's just building those two arrays like we did in the last example. And now we get to the merging stage. And what did that merging stage consist of? Let's do another example to see what will happen here. So for example, let's consider a left array that consists of the values 4, 7, and a right array that consists of the values 1, 2, 3, 5, and 6. Now I'm being a little bit more general than I've stated above. I've stated in the previous example that we split it in half and we've got our two arrays, we sort them, and then we go to merge. So we've got these two sorted arrays of roughly the same length. Here I'm just being a little bit more general. I'm just saying maybe the two arrays are of vastly different lengths. One is length 2, one is length 5 in this case. The idea though is we've got a left array and a right array. They've been sorted. Now we need to merge them together. So I want to merge these. I want to merge them into a sorted array. So how do we do that? So again, both of them are sorted, and that's the key part to this discussion. So I'm going to have a couple of pointers. They're going to start at the first value or the first term in each of these arrays, and I'm going to also have a pointer for the array that I'm filling these values into. And so what I do is I just look at the two pointers in L and R, and I say which one's smaller. And that turns out to be that value 1. So I pop the value 1 in where that pointer is pointing in our A. And then what we do is we bump up our pointers. So now I've dealt with that 1, so that pointer moves on. And I've filled this spot in A where the pointer is pointed at, so I move that pointer on. And then we just do it again. So the two pointers, the one in L and the one in R, I see which one of those is smaller. And I see the value 2 is smaller. So 2 is going to go there. And then I just advance my pointers. So again, I use the one from R, so that pointer moves on, and it points to the new spot that I want to fill in my array. These pointers are what I've indicated in the algorithm as IJK. I is the pointer in the left array, J is the pointer in the right array, and K is the pointer in the array that I am filling in. So then we'll continue on and go and do the next part. So my pointers in L and R, one's pointing to 4, one's pointing to 3. Which one's smaller? It's the 3, so it fills that spot. And now my pointer moves on. And that was the 3 that got used, so the pointer moves on. Of 4 and 5, it's the left array whose value I'm going to use there. And so now the pointer moves on, and it's the pointer in the left array that moves on. And now I look, 7 and 5 are the ones that are indicated. 5 is the smallest one, so the pointers now move on. This one moves on, and this one moves on. 6 and 7, 6 is the smaller value, so we fill in 6. this pointer moves on. This one in the top, it's now out of the array. So it means we've finished with one of the arrays. So that means, since I'm done with one of the arrays, then it's the tail end of the other array that I use to fill in the remaining spots. So I would go 7, and then I'd move this arrow on if I had to, this pointer on. It's off the array now, so now I've completed both of them, and we are done. And this one is now off as well. So that's the merge part of the algorithm. And the bulk of the work for that is happening right in here. This is where all of that merging stuff is happening. It's comparing the values of each array at the given pointers, depending on if L is smaller or the value in R is smaller, it populates that in the array. So if L is the smaller one, it throws that into our array. If R is the smaller one, it throws that into the array. And then it bumps up the respective pointers depending on which one it used. Once you've exhausted one of the arrays, either the left one or the right one, it just piles on the remainder of the other array onto the back end of the array A. And so that's the merger. And so what we'd like to know is, what is the cost to do this? How many comparisons get made? The comparison line is line 12. So we're going to figure out the cost of running this algorithm by just figuring out how many comparisons get made. So what we'll do is we'll let M, N1, N2, where N1 is the length of one half of the array, or the left array, and N2 is the length of the other array, the R array. So this is, what is the cost of merging an array, a sorted array of length N1 with a sorted array of length N2. So be the number of operations, and in this case our operations are comparisons. So this is line 12. So it's the number of comparisons to merge the two sorted arrays. Do we know anything about it? Well, what's the worst case scenario? We actually did the worst case scenario in this example. We just have to count up how many comparisons we did. So how many comparisons did we do in total? Probably would have been a good idea to keep count of this, but we can do that fairly quickly here. We were comparing 4 and 1. That was our first comparison, and that put 1 in the array. Then we compared 4 and 2, so that was comparison number 2, comparison number 3, comparison number 4, and then that put 4 in the array. So then we compared 7 and 5, that's comparison number 5, and then 6 and 7, that was comparison number 6. So we did 6 comparisons. In general, the number of comparisons that it will take is, if we really have to compare everything until we get down to the final value, which we just stick on the end. So the maximum, I'll put, it's less than or equal to, so the number of comparisons at worst case, we have to do N1 plus N2 minus 1 comparisons. So at least we have an idea of how many comparisons get done in the merging part of the algorithm. Then we also have to check the number of comparisons in the recursive part when we've done the splitting up and we sort the individual pieces. So that's the next part we want to talk about. So that's the merger. How about the splitting up part? So here's the merge sort algorithm as a whole. So what it does is it takes in an array, and then it takes in 2 indices, the left indice and the right indice, and that's what we're going to sort between. We're going to sort from AL all the way up to AR. And so that's what it shows here. This will sort AL through AR. If R is less than or equal to L, it means we don't have anything to sort. It's either 1 or no elements. So that just is a quick return. So nothing to sort. nothing to see here, nothing to do here. So then what do we do? Well, we're going to assume now there is something to sort, and that's the next stage. So what we do is we basically split at the middle index. So that's the L plus R over 2, made that M. That's our middle index. And we're going to do two things. We're going to sort the left half of the array, that's from L to M, and we're going to sort the right half of the array from M plus 1 to R. And we do that by doing a recursive call. We call the algorithm again on those smaller pieces. That will return those two pieces sorted, and then we merge those two sorted arrays together, and that has now produced the sorted whole array. So let's figure out what the cost is to perform this algorithm. How many comparisons get made? So we'll let Cn be the number of comparisons to sort an array of length n. So what is Cn equal to? Well, we just need to figure out what's going on at lines 6, 7, and 8, because those are where the comparisons are happening. So to sort the array of length n, we've split it up into two arrays, one of length n1, one of length n2, our left and right arrays. So the cost of sorting an array of length n would be the recursive call to sort the left part of the array, and the cost in doing that is C of its length, which is n1, plus the cost of sorting the right half of the array, which is C n2, plus the cost or the number of comparisons in merging those two sorted arrays. And so there's our relation, which tells us how the cost of sorting an array of length n is related to the cost of the steps involved in doing that. Now what we'll do is, for simplicity, we will assume that n is some power of 2. Now the reason I'm going to make this assumption is because if we think about what's happening, at each step I split the array into two, and then I sort the individuals. But each of these individuals I'll recursively call, so I'll split those into two, and I'll split those and those and those into two. So at each time I'm halving the length of the array. So if I assume that the length of the array is a power of 2, then it means that it's quite straightforward to split it in half each time. So I won't have to introduce any uneven sized arrays. So for simplicity, we'll assume that n equals 2 to the k. So then what does that mean? It means that Cn is equal to, well, the length of the first half of the array is n over 2. The length of the second half of the array is also of length n over 2. And merging, well, we're merging a sorted array of length n over 2 with a sorted array of length n over 2. Now what are these things? Well, we know that Cn over 2, well, it appears twice there, so that's 2 Cn over 2. We also know that m n over 2, n over 2, we know the worst case scenario for that. We know the maximum number of comparisons, so I'll put a less than or equal to. The maximum number of comparisons is, I'll put it right here, it's n1, which is n over 2, plus n2, which is n over 2, minus 1. And so that's just n minus 1. So we get plus n minus 1. So in other words, the number of comparisons to sort an array of length n is, at worst, twice the number of comparisons in sorting an array of half the length, plus n minus 1. So there is our recurrence relation. And that's what we're going to want to solve. We're going to want to figure out what is C of n that satisfies this recurrence relation. Now there's an inequality there, of course, but this is a worst case scenario. So if we just replace that with an equality, then we get an upper bound on the number of comparisons that get done to sort an array of length n. Now the first thing we should observe is this is not a recurrence relation we've seen before. This isn't a first order. This isn't a second order. What this is it's telling me that the nth term of our sequence is related to the n over 2 term. So the 8th term is related to the 4th term. The 10th term is related to the 5th term. The 100th term is related to the 50th term. So it's not a first order, second order recurrence relation. It's not a third, fourth, fifth order recurrence relation. So we can't use those techniques. At least not at first glance. The characteristic polynomial approach, that's out the window. We can't do that. But maybe we can use that iterative approach. And that's what we will do. So we're going to solve this recurrence relation, and we're going to do it using that method of iteration. So what is our approach for solving this? Well, we write out the recurrence relation for n. And then we write it out for smaller values. What smaller values? Well, I'm focusing on this one. I know that Cn can be expressed in terms of Cn over 2. So that's my next equation I'll write down. Is Cn over 2. What is that? That is twice Cn over 4 plus n over 2 minus 1. So there's the recurrence relation with n replaced by n over 2. And we can continue doing that. We've got Cn over 4 is less than or equal to twice Cn over 8 plus n over 4 minus 1, and so on. All the way down to, well, what are we going to get to in the end? We're going to get down to C2 is less than or equal to twice C of half of 2, which is 1, plus, and then it was 2, so the n value, minus 1. And then we could continue on going and get what C of 1 is. In this case, it's an initial condition, write down the last equation, but I could also use the fact here that C1 is 0 and just pop it in to that expression. So here I've written down the recurrence relation a bunch of times for these smaller and smaller values of the indices. And one thing to keep in mind is that n we're assuming is a power of 2. So this is what we're assuming. N is 2 to the k. Alright, so remember what our goal is then, is to sum up all these equations, hope we get cancellations, and end up getting an expression for Cn. This is our method of iteration that we've used for first order recurrence relations. Now how do we do that in this case? Well, I'd really like this expression, when I do the sum, to cancel with this one. The problem is, this one has a 2 in front of it. This one doesn't. So I'll put a 2 in front of it. So I'll scale through this equation by 2. And when I do that, I end up getting a 2 squared Cn over 4 plus 2 times n over 2, that's n minus 2. Now, this one's got a 2 squared in front of it. This one doesn't. So I'd really like a 2 squared in front of it, so when I sum them up, they cancel. So I put a 2 squared in front of that, which means I'm putting a 2 squared in front of this side. And so this becomes a 2 cubed Cn over 8 plus 2 squared times n over 4, that's just an n again, and then minus 2 squared. I see that these are going to be powers of 2, so I'm going to put a 2 to the 1 up on that one as well, just so we can start to see a pattern emerging. And I can even go back up to the top and maybe even put some things to indicate the pattern. This is a 2 to the 1, and this here we can think of as a 2 to the 0. And so now we start to really see a pattern emerge. We continue on going. So then I just need to know what power of 2 am I going to need on this one. Well, if I think about what power of 2 I'm going to need there. I'm just noticing that what's sitting under the n here, in that case it was a 4, in the case before it was a 2. What's sitting under the n, maybe I'll use the pointer instead. So what's sitting under the n here is a 4, or a 2 squared, and that's what's out front. What's sitting under the n here, oh, well, I don't have it written as n over something, it's just written as 2. Ah, but n is 2 to the k. So I could think of 2 as 2 to the k divided by 2 to the k minus 1. So this is really a 2 to the k minus 1. And then what's sitting out here is just 1 more than that, so that's a 2 to the k. And maybe I'll, instead of throwing these things all onto the same spot, I will put it like this. We put a 2 to the k minus 1 out in front, so really that's what happened here. We scaled through by 2 to the k minus 1, and so now I can work out that right hand side. It's a 2k c1, and then plus a 2k minus 1 times 2, but that's just an n. So we've got an n there, and then minus a 2k minus 1. And there's our full pattern. So when I sum these up, what do we get? We get that this cancels with this cancels with this cancels, something in the dot dot dot, something in the dot 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 cancels with this, and this is 0 because of our initial condition. So what survives? Well, on this side of the inequality, it's only the Cn that survives. So we get Cn is less than or equal to, and then all of the stuff on the other side. Well, I had an n, those are a bunch of n's that all add up. How many n's are there? Well, it's how many equations I've written down. I can count the equations by just thinking of this as a 2 to the 0, 2 to the 1, 2 to the 2, all the way up to 2 to the k minus 1. So there's k equations written out there. So when I sum them all up, I get n plus itself k times. So I get an nk. But then I also get negative 1 minus 2 to the power of 1 minus 2 to the power of 2 all the way up to minus 2 to the k minus 1. So I get minus 1 plus 2 squared plus dot 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 all the way up to 2k minus 1. That's a geometric series. We have a closed form for it, so that's nk minus, that'll be 2k minus 1 all over 2 minus 1. But 2k, that's just n. Up in the top right corner there we had n was 2k. So that this becomes then C of n is less than or equal to n times k. Well, what is k? So again, we'll look at the top right corner. If n is equal to 2 to the k, then k is equal to log base 2 of n. So what I have here is that this is n log base 2 of n minus n plus 1. And so there we go. And this was where k was equal to log base 2 of n. So what we found is that worst case scenario, the number of comparisons that get made for sorting an array of length n is n times log base 2 of n minus n plus 1. And if we scroll back, we see that this is exactly what we had written down here. So we've just verified this now. The number of comparisons to do merge sort is n log n minus n plus 1. And so it does a faster job, or at least it does the sorting with less comparisons than bubble and selection sort. So this is an example of what we call a divide and conquer algorithm. The way this algorithm worked was it split the problem up into smaller subproblems, solved those subproblems recursively, and then reassembled the solutions. What a divide and conquer algorithm is in general is a problem that does precisely this. It takes a problem, let's say the problem has size n, and it splits it up into a subproblems, where a is just some number. The number of subproblems is going to be at least 2. So you take your problem, your one problem of size n, split it up into 2 or more subproblems of some smaller size. We'll say the smaller size is n over b. So we've got a problems of size n over b. Then we solve those subproblems, and we use a recursive call to our whatever our algorithm is that's designed to solve the problem. It now gets called recursively on those subproblems. That's the divide and conquer. You divide up into smaller subproblems, and then you solve those smaller subproblems, and then you reassemble to get the solution to the original problem. Now, what's the cost in performing a divide and conquer algorithm? We can do the same procedure that we did for the Mergesort algorithm. We can just be a little bit more general here. So let's figure out what is the cost in doing this. We'll let Fn be the number of, in the Mergesort it was comparisons, but in general we'll just say let it be the number of operations. So it's the number of operations to solve a problem of size n. So that's what we're interested in. What is f of n? We'll also let h of n be the number of operations in, while doing two things: splitting the problem up, that's the problem of size n up, into the a smaller subproblems, and then combining those results after you've done the solution of the subproblems. So in other words, this is steps 1 and 3 above. The number of operations in steps 1 and 3. So Fn is the number of operations in solving a problem of size n. Hn is the number of operations in splitting the problem up into smaller pieces and then recombining back to the original solution. So what do we have in this case? Well, we have that, let's say then, Fn, the number of operations to solve the problem of size n. We've just split it up into a subproblems, and each of them are size n over b. So how many operations does it take to solve a subproblem of size n over b? It takes Fn over b operations. And I had to do that for each of the a subproblems. So there's a times Fn over b operations to solve those subproblems, plus the cost of disassembling and reassembling the step 1 and 3. So that's plus an Hn. And so there is our recurrence relation. We have that this is valid for n bigger than or equal to 1, and we assume that f of 1, so to solve the problem of size 1, it's going to take some fixed number of operations. So we assume this is some constant. So that's some constant. And as before, to make the analysis simpler, we assume n is some perfect power of b. Because we are taking n and the subproblems are going to be of size n over b, and then we want to do that again, so it would be n over b divided by another b, so n over b squared, and then when we would do it again, n over b cubed. We just want to make sure that those are integers to make the analysis easier, so we'll just assume that the size of the original problem was some perfect power of b. And so that's what we're interested in solving. So for a divide and conquer algorithm, the number of operations to perform the algorithm, it's a recursive algorithm, the number of operations is given by this recurrence relation. And so to figure out what the cost is of running the algorithm, we would need to solve this recurrence relation for f of n. Now, in the notes that I've alluded to at the start of this lecture, we have provided a full solution to this recurrence relation, and you can look through that for the full details. We've given what's essentially the fundamental theorem of divide and conquer algorithms. It tells you for any divide and conquer algorithm, this is the cost of running it. And so we've written out the solutions based on the cases of how A and B are related to each other. However, in this lecture, we'll just go and do some examples. We already have seen one example of solving a divide and conquer algorithm. In this case, it was a merge sort, and we saw there was our recurrence relation, much the same form as the one we've just worked out generically. In this case, b is equal to 2 because the size of the subproblem was n over 2 in this case, and the number of problems that we split it up into was 2 problems. So one problem split into 2. So a is 2, b is 2, and in this case, hn was n minus 1. And we solved that, and we got our solution. Let's look at another example of a divide and conquer algorithm. So in this case, we'll just look at a divide and conquer algorithm that's designed to add up an array of numbers. So here we've got our algorithm called add. We input an array of length n. So there's our array of length n. And it's going to return the sum of those numbers. Let's just look at an example of how our algorithm is going to work. So we've got an array. It's 9, 1, 3, 7, 2, 2, 6, 1. Let's just say that that is our array of numbers that we wish to add up. So there are 8 numbers there. The way we are going to do it is we are going to cut the array in half. We are going to make a recursive call, sum the first half of the array, sum the second half of the array. So the first half of the array, that will sum to, so 9 plus 1 is 10, plus 3 is 13, plus 7 is 20. So that's our S1. We'll also sum the second half of the array. 2 plus 2 is 4, plus 6 is 10, plus 1 is 11. And then we will add the values of those two sums. So that's 20 plus 11, or 31. How many operations did it take to do that? That's what we want to count. So this is what our algorithm is going to do. It's going to split the array up into 2 smaller bits, sum each of the individual bits, and then reassemble the final sum. But if you think about how, I wrote down S1 as 9 plus 1 plus 3 plus 7, but the way our algorithm is going to perform that step is it's going to go as follows. It's going to say, oh, you want to sum the first 4 numbers of the array? Okay, let's split that array in half, and we'll sum the first 2 and the second 2. And then it says, oh, you want to sum the first 2 numbers in the array? Okay, let's split those down. And so it's going to recursively split this thing down and do these sums and then reassemble. So that's the recursive nature of the algorithm. What we want to do is we want to figure out how many operations this algorithm does in order to add all of the numbers. What is our operation we're going to count? We're going to count additions. So how many additions get done in order to add these numbers? So we're going to let an be the number of additions to add an array of length n. For simplicity, since we are going to be splitting it down, halving it and then halving it again and halving it again like I've done here, it makes things easier to analyze if we assume that the length of the array is a perfect power of 2. So for simplicity, assume n is equal to 2 to the power of k. So that means when we do this splitting, so we're going to take our original array of length n and we're going to split it into 2 arrays. So the length of the first array is going to be n1 that's n over 2. And the length of our second array, which is n2, that's going to also have length n over 2. So these are the lengths of each half of the array. Okay, so that's indicated here. N1 and N2 are the lengths of each half that we are then going to sum individually. And so we just notice that for simplicity, we'll make those n over 2's, both of them. So what is our recurrence relation on an? So then we have that an is equal to, so how many additions get done in adding an array of length n? Well, those additions happen in these lines. Line 7, line 8, and line 9. Those are where the additions happen. So how many additions get done in line 7? Well, there we do a recursive call to the add function, and we call it on an array of length n1. But n1 is n over 2, so what this is it requires a sub n over 2 additions. That's our line 7. What about line 8? Well, it makes a recursive call to the add function for an array of length n over 2. So it's going to do this many additions, a sub n over 2. So that's line 8. And then line 9 sums two numbers. So there's one addition that happens in line 9. So we've got a plus 1 there. And so this tells us then that an is 2 times an over 2 plus 1. And that's for n greater than or equal to 2. Moreover, what do we have for, so then I'll say and a sub 1. How many additions happen if our array has length 1? Well, that's where we scan through and say, okay, if we called the add function on an array of length 1, then n would be 1. And if n is 1, then just return the first value. So don't do any additions. So a1 is 0. And so there's our recurrence relation for an along with its initial condition. And that's what we want to solve. So now we'll solve this. Solve the recurrence relation. Again, it's not a recurrence relation that we've seen in previous lectures. It's not a first order recurrence relation, a second order. It's not one of these things that we had methods for dealing with in general, but it is a recurrence relation that comes from the divide and conquer algorithm. And so we can use those same techniques that we did for the previous one, the Mergesort one. We use that method of iteration. So we'll write out a sub n is equal to 2 a sub n over 2 plus 1. And then we'll rewrite out the equation, in this case for a n over 2. So that's 2 times a n over 4 plus 1. And then a n over 4 is 2 a n over 8 plus 1. And so on, all the way down, until we get down to a2 is equal to 2 times a 2 over 2, which is a1, plus 1. And then a1 is equal to 0. And we could include that here. I didn't include this last line in the Mergesort one because I just put 0 in for a1, but just by way of contrast, we could add it as the last line. So I'll just do that here, just so we can see an alternate way to deal with that initial condition. Now what I'd like to do is sum these all up. So I'd like to sum them. The problem is, at this stage, I'm not going to get the cancellation I want because I've got 2 an over 2's here, but only one of them here. So this is where we have to adjust for those factors. I have 2 an over 2 on the right, so I'm going to have to make this one a 2, which means I'm going to scale through this by 2, and so it becomes a 2 squared, an over 4 plus 2. Now I've got a 2 squared in front of an over 4. so I need a 2 squared in front of it on the next line. So I'm going to have to scale through by 2 squared. And so we have a 2 cubed an over 8 plus 2 squared. And again, I can adjust my exponent in the line before. That's 2 to the 1. And I can look at this one up here as a 2 to the 1 and this one as a 2 to the 0, just to get the pattern going. And then we keep going. This would be a 2 to the k minus 1, 2k minus 1. So that's a 2k a sub 1 plus 2k minus 1. And then I would put a 2k in front of this one and a 2k, and that's still just 0. And so now we can go ahead and do the sum. I'm going to get lots of cancellation. I'm going to get this cancels with this cancels with this, and so on, the usual all the way down. And so what survives on the left-hand side is just the a to the n. So we get a to the n is equal to, what's survived on the right side? Well, I've got a 1, or a 2 to the 0, 2 to the 1, 2 to the 2, all the way up to 2 to the k. So I get a 1 plus 2 squared plus dot 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 all the way up to 2k minus 1. That's a geometric series, so that has value 2k minus 1 over 2 minus 1, or in other words, its value is just 2k minus 1, but 2k is n, so n minus 1 is our final result. We assumed n was the perfect power of 2. So there we go. It says that our divide and conquer approach for summing up these n integers cost us n minus 1 additions. And if we think about it, that's not a surprise, because when I look at how I did it, what I would do is I'd split it up into 2 halves, do the sum of the 2 halves, and then I have this sum here at the end. That sum corresponded to sort of this vertical bar between the 2 halves. So this vertical bar corresponds to that final sum we did. But then I would have also done this sum here, corresponding to that vertical bar on the recursive step. And then I would have also done this one and this one. So in effect, I'm actually going to do a sum corresponding to each one of those vertical bars. And since there are n values, there are n minus 1 vertical bars between them. So I would have done n minus 1 sums. So I could see that from just the process of how this works, but we also verified it by setting up the recurrence relation and solving it as well. All right, well that's it for this section, and that's it for recurrence relations. So thanks very much for watching, and we'll see you again next time.